Hello everybody. Today I'll be discussing on the topic scheduling of irrigation under the course AGRON 504 Principles and Practices of Water Management. So basically we know that irrigation is the artificial application of water to the soil, usually for assisting in growing crops. Now the water that is supplied to the crop, it may be either through irrigation or maybe through in the form of rainfall. Now, basically we apply irrigation to replace the missing rainfall periods or maybe the drought period to prevent the yield loss, to prevent the plants from going under stress, and sometimes maybe to protect the plants against frost. Now, if we look, irrigation has basically two primary objectives: to supply essential moisture for plant growth, which includes transport of essential nutrients, and sometimes in a saline condition we apply irrigation or maybe excess amount of water to leach or dilute the salts in the soil and leach them out from the system. Now if we look at the soil water, we can see that we all know that within a soil profile, after irrigation the entire soil profile is saturated. Here we can see that this is the saturation point when all the macro and the micro pores are totally filled with water. Now due to the action of gravity, as the water drains out from the macro pores, so the excess water present in the soil, under the force of gravity, it starts draining out from the soil. So after some time the soil reaches a condition which is known as field capacity, where the water present in the soil is only held within the micropores and all the macropores have been drained out from of water. Now at field capacity, we know that field capacity is also known as the uppermost limit of plant available water. Now when the soil is further drained out, that means the water present in the soil is either lost in through evaporation or maybe transpiration or through deep percolation. So after some time a status is achieved which is known as permanent wilting point. Now this permanent wilting point is also known as the lowermost limit of plant available water. What happens here is that beyond this point, if we do not apply irrigation, then the plants will ultimately die. So basically the water present between field capacity and permanent wilting point, this is available to the plants. Now beyond permanent wilting point, there is also a limit known as oven dry, and within permanent wilting point and oven dry limit, this part of water is unavailable to the plants. Likewise, the water present between saturation and field capacity, this excess water, this is also not available to the plants because plants cannot take up this water from the soil. So basically the available water is the water present between field capacity and permanent wilting point. Now there is also a term known as MAD, management of allowable deficit. Now the percent deficit of available water that management will accept, which means that whatever iterations or kind of management practices we can assume, it has to be within this field capacity and permanent wilting point limit, because this water is available to the plants, and here we can determine that how much water we can save through irrigation, proper irrigation application, that is not applying excess water so that the soil goes above field capacity, and not applying too much less water so that the plants face stress condition, as the water level goes beyond permanent wilting point. Now, if we see the available water, it it has a variable range and it varies with the kind of soil. We can see that a sandy soil has the least range of available water, and it gradually increases with clay soil having the maximum range of available water. That means here the difference between field capacity and permanent wilting point in case of a clay soil varies at a larger value. So we can see that more the coarse texture soil, less is the portion of the available water. More is the fine textured soil, the portion of available water is higher. Now, if we look at the effective rooting zone of a plant, this is a generalized picture depicting the rooting zone of a plant. We can see that majority of the roots is present at the upper two soil layers, and the volume of the roots gradually decreases with the increase in soil depth. Now, if we look at the roots, these roots are mainly responsible for absorbing water from the soil. So what happens is that there is a thumb rule of 4, 3, 2, 1. That means the percentage of moisture extraction pattern, if we look, it shows that the majority of the water is absorbed from the top soil layer. That means 40% of the total absorbed water by a plant, it occurs from the topmost layer, followed by 30% of the total water absorbed is from the second layer, and as the soil depth increases, the root volume decreases, the percentage of moisture extraction by the roots also decreases. So this is basically a general thumb rule which shows a thumb rule of 4, 3, 2, 1. That means 40% from the top soil layer, followed by 30% from the adjacent layer, and simultaneously 20% and 10% from the lower depths. So basically, talking about today's topic, irrigation scheduling and its techniques. What do we mean by irrigation scheduling? Scheduling of irrigation is the basic idea which gives us the notion of when to irrigate and how much to irrigate. Because if we have the idea of when to irrigate and how much to irrigate, we can save a quantifiable amount of water that can further be utilized for growing of other crops, or maybe extending the irrigation limits to a much larger area. Now, scheduling of irrigation is a process to decide when to irrigate and how much to irrigate. As I was saying, that not only the timing of irrigation is important, but how much to irrigate is also important, because as in the previous slide we have seen that the amount of water available to the plants, it varies with the soil type. Now, for example, if we are adding too much amount of irrigation in case of a sandy soil, the majority of the water is lost through deep percolation, as because sandy soils have larger proportion of macropores. So they help in water conductance easily, so the water is drained out from the soil very easily rather than it is being held in the soil. In comparison, if we look into a clay soil has a higher water holding capacity. That means if we apply a large amount of irrigation to a clay soil, it can hold that amount of water. But if we apply the same amount of irrigation in case of a sandy soil, majority of the water will be lost. So how much to irrigate is very much necessary in order to get sufficient amount of water savings. Now, farmers in general, they tend to irrigate either on time interval basis or based on the physical appearance of the crops. That means farmers generally follow, like they irrigate their crop on a specified time basis pattern, or maybe they irrigate their crops based on their experience of the growth stages of the crops. And while talking about the scheduling of irrigation, there are several other approaches, that can be soil approach, plant approach, or maybe atmospheric approach or indicators, which gives us the ability to decide that when we need to irrigate our crops and how much water we need to apply. Now, basically, farmers face two kind of situations. First situation is where adequate water is available. Farmer aim to produce maximum yield per unit of land and unit of water. Here he has to provide optimum irrigation schedules with time sequence for number of irrigations and quantity of each irrigation for ensuring optimum crop yield with high water use efficiency. So the first condition is where the water is not limiting, whereas the land is limiting. While the second situation is where the water is limiting. So the farmer's main objective would be to get maximum yield per unit of water, where the shielding is very much important. Now, what are the advantages of irrigation shielding? It enables the farmer to schedule water rotation among the various fields to minimize crop water stress. It reduces the farmer's cost of investment by saving water as well as labor investment. Moreover, when we apply huge amount of irrigation, what happens is that it dilutes the salts or maybe fertilizers, and it leaches the fertilizers from the soil zone or root zone. So if we apply limited amount of irrigation, what happens is that the loss of fertilizer is saved, thereby it prevents the fertilizer cost. Moreover, it also minimizes the waterlogging problem, root zone salinity problem, and the water saved through shielding irrigation could be used to irrigate non-cash crops. Now, the irrigation shielding methods, it may range from qualitative approach to quantitative approach. Qualitative approach mainly means based on the experience, looking at the soil condition or the soil status or maybe the plant growth stage, we may schedule irrigation, we may decide that when to irrigate and when not to irrigate. Quantitative measures mainly involves water budgeting based on the soil moisture content or maybe the atmospheric condition or maybe the plant water status. So scheduling of irrigation, it has three major approaches. One that I was telling, soil water regime, other is the climatological approach, the third one is the plant indices. Now under soil water regime, we have three different kind of approaches. First is the feel and appearance method, which is basically a qualitative measure. Depletion of available soil moisture. Here this is quantitative because we need to measure the amount of water present in the soil before we decide whether we need to irrigate the crop or not. The third soil water regime approach is the soil moisture tension. By measuring the soil moisture tension or the soil water potential, we can decide based on the past experiences or the researches conducted, we can decide that which is the best time to irrigate a crop and at what soil moisture tension beyond which the crop would not face any kind of stress. Within the climatological approach, there are two approaches. One is cumulative pan evaporation and IWCP ratio, and under the plant indices, we have the visual symptoms, that is a qualitative approach, soil climb mini plot technique, growing excessive plant population, growth rate of the plant, relative water content, plant water potential, canopy temperature, using of indicator plants and critical growth stages, majority of the which are quantitative measures except for visual symptoms and critical growth stages, where based on the experience, farmers or researchers tend to make the decision when to irrigate a crop. Starting with the soil indicators, these methods involve in determining moisture content of the soil and finding the deficit level in available moisture. So if you remember previously when we were talking, the available water ranges between field capacity and permanent wilting point. So whatever kind of alterations or modifications that we plan for scheduling of irrigation, it all ranges between that field capacity and permanent wilting point. Now, based on the predetermined minimum water content, irrigation can be given to bring the soil back to field capacity, or maybe the soil content is determined either by direct measurement or by indirect measurements, and based on that we can decide when to irrigate. So the basic method of estimating soil moisture content is the gravimetric method. I hope we are very much familiar with this. Here what we do is that we take a fresh soil sample from the field, we weigh it, then we oven dry the soil until it obtains a constant weight. Then we again take the weight of the dry soil, and now the gravimetric moisture content is calculated based on the formula fresh weight minus dry weight of the soil upon dry weight of the soil multiplied by 100 in terms of percentage. So basically this is the amount of moisture present in the soil upon the dry weight of the soil multiplied by 100. So this gravimetry moisture content method, this gives us a direct estimation of the amount of water present in the soil on weight basis. That means gram moisture per gram soil. And with this we can get a direct idea of how much moisture is present in the soil. This method is basically a destructive method of soil sampling where, and it is also simultaneously time consuming. The next approach is feel and appearance method. This is basically used by the farmers to judge the soil water content based on the feeling of the soil, and then they make their judgment whether it is necessary to irrigate the crop or not. This method is basically a quantitative measure. It does not give us the exact estimate of the soil moisture content. However, based on the experience, we can often determine when it is best to irrigate. Now, there is a guide for judging the amount of available moisture in the soil. It varies from soil to soil. So what happens is that we sample some amount of soil with the help of auger or maybe with the help of hand, and then out of that soil balls are made, and based on the consistency of the balls made, it is determined whether it is necessary to irrigate or not. For example, for a coarse texture soil at field capacity, on squeezing no free water appears in the soil but wet outline is left on the hand. This is also similar for other textured soil. But at 75 to 100% of field capacity, in case of a coarse textured soil, it tends to stick together slightly, sometimes forms a very weak ball under pressure. That means after we form a ball in our hand, the soil tends to break in case of a coarse textured soil, whereas in case of a fine textured soil like silty clay loam or clay loam type of soil, we can make ribbons out of the soil which has a slick feeling. So based on this, it can be estimated that it is somewhere between 75 to 100% of the field capacity. Now, this approach also has a loophole, that is, if we do not have sufficient experience, the problem is that we could underestimate the soil water status, which might result in plant water stress and ultimately hampering the crop yield. Another method is the tensiometer method. Now here in the right hand side, if you look at the figure, this is a picture of a tensiometer placed at two different depths of the soil. Here it has three basic components. One is the pressure gauge, which measures the pressure inside this tube, and a ceramic cup which facilitates the exchange of water present inside the tube with the surrounding soil. Now based on the moisture content of the surrounding soil, as this ceramic cup is porous in nature, there is an interaction of water. So if the soil condition around the ceramic cup is drier, water will flow out from the ceramic cup into the soil. And now, since the tube is sealed with a cap on the top, the tube will tend to develop some kind of pressure inside it, which is then recorded with the help of this gauge, pressure gauge, and it is measured in centibars. So this pressure gauge basically has a unit from 0 to 100 centibar, which is equivalent to 0 to 0.1 bar, 0 to 1 bar. Now, as the water moves out from the tube, so this pressure is generated inside the pipe. Now, based on that measurement reading or the pressure reading or the soil moisture potential reading, we can determine when to irrigate and when not to. And basic idea between the placing these two tensiometers is that it helps us in determining the flow of water within the soil, and also simultaneously it gives us an indirect measurement of the water status of water in the soil. So while scheduling of irrigation based on this tensiometer method, we can determine when to irrigate based on some specific values corresponding to some specific crops, which helps us in scheduling of irrigation. Now this tensiometers for this reason is also known as aerometers, as because they help us in scheduling irrigation. Now the electrical resistance method. Sometimes we often use porous blocks or maybe gypsum blocks which are placed in the soil, and as because we know that gypsum blocks can absorb moisture, it helps us in determining the amount of moisture present in the soil. Now the basic principle is that this gypsum block, it absorbs moisture due to its porous nature, and as we know that water is a good conductor of electricity, so it measures the electrical resistance between two ends of a gypsum block, and these readings are then converted into the soil moisture status of the soil based on some equations, and we can measure the amount of moisture present in the soil, which again helps us in scheduling of irrigation. Another approach is the water budget technique. So it is done basically by computing the everyday evapotranspiration, effective precipitation, soil water content. Although this method is cumbersome and requires a lot of data, but in this approach, we take into consideration all the factors, that is the water present in the soil, the kind of weather condition that is prevailing, and also we take in consideration the plant factors, because with stage, as the plant grows, the evapotranspiration from a plant, it changes over time. So it gradually increases from sowing up to harvesting. So in this water budget technique, we take into consideration all the three things. Now, if we see, this is a representation of a dynamic model of the water budget or the water and its flow within the soil, plant and atmospheric system. So we can see that this is the soil and the plants are planted here. So water present in the soil is lost through evaporation, through transpiration. From precipitation, the water is received by the soil, or maybe from irrigation. Now, there are other loss factors like runoff and deep percolation. So these are the factors which we need to consider by deducting it from the total water that we are applying. Now there is another contributory factor, that is the capillary rise. That means if we have shallow water table, so capillary rise contributes a handsome amount of water towards the plant growth factor, which is further utilized by the plant for evaporation and transpiration. Now, as I was saying, that from sowing through the total crop growing period, So basically, based on the plant area or the leaf area, the evapotranspiration changes. Now, as the evapotranspiration changes, so with the plant growth, there is also increase in the root mass. So the amount of water being extracted by the plants for transpiration purpose or the amount of water being lost from the soil through evaporation, it changes with time and also with soil depth. Now in the water balance approach, as I was saying, that irrigation, precipitation and capillary rise, these are the input factors, while evaporation, transpiration, deep percolation, runoff, these are the loss factors. So soil water can be summarized as the changes in the soil moisture status. That means initially what was the soil moisture status and finally what is the soil moisture status. So this is basically the change in soil water. Amount of water received from irrigation, amount of water received from rainfall, water received through capillary rise minus the water lost through evapotranspiration, deep percolation and runoff. So this total equation gives us the water balance for a field for a crop. Now previously as I said that the water present between field capacity and permanent building point. So between this water, this is the total available water to the plants. Now somewhere between midpoint between field capacity and building point, it is known as readily available water. Above the field capacity, it is known as saturation, or the water is superfluous water which is not available to the plant. And this total range of water present between field capacity up to the hygroscopic point, this is known as capillary water. So now this portion of readily available water, that means somewhere midpoint between field capacity and between building point, so the middle point between field capacity and building point, this range is known as readily available water. So we can juggle with this portion of the soil in order to schedule the irrigation and also simultaneously take care of the water savings. Now the percentage of available soil water which can be depleted between irrigations without serious water stress, this range lies between the readily available water. And the values for readily available water as a percentage of total available water, it varies between 25 to 40% of the total available water. That means the readily available water, 25 to 40% of the total available water is the readily available water for high value, shallow or sparsely rooted crops. In case of deep rooted crops, it is basically 50%, while for very deep rooted crops, it has 60 to 65% of the total available water. That means based on the rooting pattern, the range of the readily available water, it changes. For a safe level, 50% of the total available water may be referred to as the readily available water. So this is again a picture representation of what happens or from which point the deficit begins. So basically, between field capacity and permanent building point, this is the middle point. Now here, this part we can say it as the readily available water. Soil moisture variation between this range does not hamper the crop evapotranspiration or the crop growth and yield. But beyond this point, what happens is that basically the deficit begins. Now, from this middle point downwards, in this portion, in this range, the photosynthesis is slowed, the evapotranspiration is slightly hampered, but it doesn't hamper the yield significantly. But beyond this point, we can see that the points nearing to permanent building point, the crop faces severe water stress, which results in huge loss of yield. So depth of irrigation criteria, we can fix it as either we apply water to revert back the soil moisture content to field capacity, or maybe apply a fixed depth of irrigation, that is a predetermined amount of water is applied for each irrigation frequency in order to reduce the risk. If we can see it diagrammatically, we can see here this picture represents the root zone water depletion and the irrigation water supply strategies. Now here if we see that this entire range is the soil water content. Here this top dotted line is the field capacity range, the bottom dotted line is the building point, and somewhere between is the middle point, and this part is the readily available water, while from this point to this point it is the total available water. So this middle point we can say it as the allowable depletion threshold. Now what happens is that when we are allowing the soil moisture to decrease in the soil up till this point, so this range is between the readily available water limit. So here the root zone water depletion, that is the DR, it is less than readily available water, and we apply irrigation, full irrigation, to revert the soil moisture status back to field capacity. In another situation, what we can do is that we allow the soil water to deplete up to the allowable depletion threshold, and here we again apply irrigation, but not full amount of water, so that the soil water status reverts back to field capacity. That means here we are not applying the full amount of water, only certain amount of water, so that the soil moisture status is somewhere between field capacity and the allowable depletion threshold. So in this case we are applying partial irrigation. Another strategy could be we allow the soil moisture to decrease beyond the allowable depletion threshold, and then after reaching a certain point we again apply full irrigation to bring the soil back to field capacity. Here that we are allowing the depletion of root zone water to be more than readily available water. So here if we look at this point, that means had we applied irrigation at this point, so this would have been full irrigation, but instead of that we are allowing the water to deplete for some more time, so that it goes beyond the allowable depletion threshold. So this strategy is basically a sort of deficit irrigation strategy, where we are further delaying the application of water by allowing the soil water to decrease beyond the readily available water limit. So what we can see is that this portion we are allowing the crop to go under stress by giving it deficit irrigation in terms of delaying the irrigation or delaying the irrigation time. Now if we can delay the irrigation time, what will happen is that we are allowing some amount of water stress, but we also need to keep in mind that this stress doesn't hamper the crop yield. By this approach, what we can do is that we can reduce the number of irrigation, or indirectly we can reduce the amount of irrigation water that is being supplied to the crop, thereby reducing the water supply and also maintaining the relative yield. So what this helps is that this helps in water savings without quantifiable decrease in crop yield. So if we look at this theory diagrammatically, we can see that the relative water consumption, so as the relative water consumption increases, the relative yield also increases, and at 100% water consumption there is 100% yield, that is actual yield upon yield, maximum yield. So this axis gives us the idea of actual yield upon maximum yield, while this axis x-axis gives us the estimate of the actual crop evapotranspiration upon maximum crop evapotranspiration. So as we know that if we supply sufficient amount of water that is required by the crop, we can, that means at maximum crop evapotranspiration, we can gain maximum yield. While at the actual crop evapotranspiration, we get the actual yield. So 100% of etc max gives us the maximum yield. Now, if we can decrease the relative water consumption through deficit irrigation strategy, we might see that with 20% reduction in water consumption, there is only 5 to 10% yield reduction. That means the water reduction is more compared to the yield reduction, which is more beneficial in those areas where the water is limiting. That means here the water savings is significant compared to the yield reduction, which may be or might be, may not be significant. So deficit irrigation strategy basically says that if we want to get 100% of the yield, we need to operate full irrigation at this point where we can get the maximum crop evapotranspiration. However, if we want to reduce the crop evapotranspiration but not significantly the yield, for deficit irrigation strategy, we need to apply the irrigation somewhere in this region where the crop evapotranspiration or ETC is reduced, but not the without the significant reduction in yield. Now the second parameter for scheduling of irrigation is the climatological approach or using the meteorological indicators. Here in this method, the soil moisture is supplied based on the calculation of the evapotranspiration or maybe the evaporative demand of the atmosphere. And this is basically dependent on the meteorological indices like the temperature, the wind speed, or the humidity present in the atmosphere. And this is not a direct measurement of the soil moisture status, but here we quantify the amount of evapotranspiration that is occurring in the atmosphere, and based on that we schedule the irrigation. So in this climatological approach, the first method is the PET measurement or the potential evapotranspiration measurement. So potential evapotranspiration can be measured from any of the empirical formulas like Planck-Creedle method or maybe the Thornthwaite method, where they take into consideration weather indices like temperature and solar radiation for determining the potential evapotranspiration of a place in a day at a time. And based on that potential evapotranspiration estimation, we can determine that we can assume that how much depletion of available soil moisture happens in the soil, and based on that we can determine how much irrigation or when we need to apply irrigation or how much we need to irrigate. Potential evapotranspiration or the actual evapotranspiration can also be measured with the help of lysimeters or through energy balance approach or by combination of the energy balance and the aerodynamic approach. Another method is the cumulative pan evaporation. Now this is a representation of the pan evaporimeter, which is very common in any agromet observatory station, where you can see that there is a large pan evaporimeter placed for measuring the daily evaporation, not the evapotranspiration, but the evaporation from a free soil, from a free water surface. So basically this evaporation from free water surface gives us the idea of the evaporative demand of the atmosphere of a place at a time in a day. Now this may vary from place to place. For example, the evaporative demand today at Sabor may not be equal to the evaporative demand at Patna on the same day, because due to the difference in the temperature, solar radiation, wind speed and the relative humidity. Because all these factors combined, they determine that how much water can be evaporated from a free water surface in a day. So giving you the basic idea, If the temperature is more, it will promote the evaporation of water from a free water surface or maybe from soil. Likewise, if the relative humidity of the atmosphere is low, that means it can absorb more and more water vapor into the atmosphere. So, it will also promote the evaporation from the soil surface or maybe from free water surface. Likewise, if the day is windy, that means there is wind conditions prevailing, so it will also promote in more evaporation. Now, based on this approach, we measure the cumulative evaporation from the pan evaporimeter for a period. So, previous research has shown that wheat requires 75 to 100 millimeter of cumulative pan evaporation under Ludhiana condition. Similarly, for sugar cane, it required 75 millimeter of cumulative pan evaporation in Maharashtra before the next irrigation is applied. Likewise, in Ludhiana conditions, green gram required 180 millimeter of cumulative pan evaporation before irrigation was required to be applied. So basically, this cumulative pan evaporation gives us a gross idea that based on certain amount of pan evaporation which has occurred, we need to apply water into the soil in order to maintain the plant health and also preventing the plant from growing under stress. Another very popular approach is the IWCP approach. Here IW represents the irrigation water and CP is the cumulative pan evaporation. In this method also, the values from the cumulative pan evaporation is used, but here the irrigation is scheduled based on the value of a ratio between irrigation water and cumulative pan evaporation. The values of the ratio may vary from 0.5, 1 or maybe 1.5. It varies based on the crop from place to place. Here the basic idea is that here the irrigation water, how much irrigation water will be applied is predefined, or the depth of irrigation water is predefined. That means suppose we have decided to apply 5 centimeter of irrigation whenever we irrigate a crop, and now the IWCP ratio we have determined it to be 1. That means whenever the IWCP ratio will be 1, we will apply irrigation. So what happens is that 5 by CPE is equal to 1, which gives that when the cumulative pan evaporation is equal to 5 centimeter or 50 millimeter, then we will apply irrigation. So what happens here is that whenever we are scheduling irrigation at IWCP ratio of 1, that means after 50 millimeter of water of cumulative pan evaporation has been measured, we apply irrigation. So here also we are measuring the daily pan evaporation and we are accumulating it until and unless 50 millimeter of water has been evaporated from the pan. Likewise, while with changing this ratio from 1 to 0.75 or maybe from 2.8, the cumulative pan evaporation values basically vary, which varies the irrigation interval or the time period between two subsequent irrigations. The third factor for scheduling irrigation is the plant indicator approach. So here the irrigation is scheduled basically based on the plant water status or maybe the physical appearance of the plant or some measurements of the water content in the plant, which gives us the indirect measurement of the whether the plant is under water stress or not. So the first approach is the appearance and the growth. For instance, if we observe that the plant is wilting or drooping or curling or maybe the leaves are rolling, we can easily understand that the plant is under stress, and if the soil is dry, then it is quite obvious that it is water stress. So these indicators can be used for scheduling of irrigation. Sometimes all plants don't show similar kind of appearance, so it could be change in the foliage color, or maybe sometimes water stress leads to appearance of carotenoids or anthocyanin pigments. In case of sugarcane, shortening of internodes is a symptom that the plant is facing water stress, or maybe in case of cotton or grapes, due to the reduction in the stem elongation or retardation of the stem elongation, it gives us the indication that the plant is under stress. So, from these physical appearances, we can determine that whether the plant needs irrigation or not. The second approach is the soil cum mini plot technique. Here, soil cum sand mini plot technique. Here, what is done is that if you have a field, a large plot, at one point of the plot, an area of 1 meter by 1 meter is selected, and the soil from 1 meter depth of that specified area is taken out and it is mixed with sand at a ratio of 5% by volume. So what happens is that whenever we are mixing sand, that means since sand is a coarse textured soil particle, so whenever we are mixing the sand with that soil, so it changes the porosity of the soil. That means sand has more macropores, and macropores conduct water more readily as compared to micropores. So if a soil has more amount of sand, so it will tend to drain out the water from the soil quickly as compared to your actual field. And now the plants are planted in that specified area along with your main field. So what happens is that whenever the water will drain out from that 1 meter by 1 meter area quickly, so the plants will show wilting symptoms in that specified area earlier compared to your actual field. So this gives us a rough estimate that when do we need to apply irrigation water by looking at the wilting symptoms in that small area. So this is basically soil cum sand mini plot technique. Next factor is the plant population technique. Here it is quite simple. From a main field, a small area is planted with 1.5 to 2 times of the optimum plant population. So what happens is that in that specified area, the evapotranspiration is enhanced by 1.5 times or it is doubled. So what happens is that compared to your actual field where the optimum plant population is maintained, in that specified area where there is more plant population, so that region of the soil will be drained out of water more quickly due to higher evapotranspiration. Now automatically the plants will show wilting symptoms or drooping symptoms earlier in that small area as compared to a main field. So by monitoring that small amount of area, you can determine whether you need to apply irrigation to your larger field or not. Another method is estimating the canopy temperature and measuring the crop water stress. So earlier what happened is that the individual leaf temperature were used to be measured. Now the extension of the temperature measurement from individual leaf to the canopy temperature to the entire plant canopy became difficult. So with the help of infrared thermometers, the canopy temperature of the plant could be measured easily, and this measurement of the canopy temperature gives us an idea that whether the plant is under stress or not by comparing the temperature to the air temperature. So basically this is a picture of a typical infrared thermometer. Infrared thermometer has various uses. It is also used in the ore industry to remotely measure the temperature of any object, or in case of agriculture we can use this thermometer to measure the canopy temperature of the plant, not the leaf temperature. So what happens is that whenever evapotranspiration is taking place, this evapotranspiration occurs in order to maintain the temperature of the plant or the canopy temperature of the plant. If there is sufficient amount of water present in the soil, plants will evapotranspire efficiently. But if there is water stress in the soil, the evapotranspiration will be reduced. By reducing the evapotranspiration, what happens is that there is simultaneous increase in the canopy temperature of the plants as compared to the air temperature. Now, a difference between the canopy temperature and the midday air temperature gives us the idea that whether the plant is under stress or not. If this difference value is negative, that means the plant is not under stress. Whereas if the difference between canopy temperature and air temperature is positive, this shows that the canopy temperature is higher than air temperature, which is indicative of the fact that the plant is under some kind of stress. Now, the basic principle of this infrared thermometer is that it is based on the Stephen-Boltzmann black body law, where R is equal to epsilon sigma T to the power 4. Here, sigma is the Stephen-Boltzmann constant, epsilon is the emissivity, T is the temperature. So, here the instrument measures the radiation released from a surface with respect to a black body or in comparison to a black body. So, basically using this formula, this instrument or this infrared thermometer, it releases the infrared radiation and then receives it back, and then it processes the emissivity, and based on this emissivity of a body, in our case which is the plant canopy, it gives us the estimate of the temperature. So now if we take out the difference between canopy temperature and air temperature, it gives us the stress degree day index. Now this stress degree day index is a very good parameter for measuring the correlation between the changes in canopy temperature and the yield. If the cumulative stress degree day index is higher or positive, it leads to lowering of the yield, while if the cumulative stress degree day index has a negative value, it promotes the grain yield, as because I was saying that canopy temperature minus air temperature, if it is positive, which it indicates that the canopy temperature is higher than the air temperature, that means the plant is under kind of stress. So this indicates that if the cumulative stress degree days is a negative value, the final grain yield will be higher compared to if the cumulative stress degree day index is a positive value. Now, the canopy temperature difference value or the stress degree day index value can also be used to trigger the irrigation or determine when we need to irrigate based on the past researches. Here you can see how a person is measuring the canopy temperature of a sunflower canopy. Now measuring the leaf water potential. For measuring the leaf water potential, a special instrument which is also known as the pressure chamber, it is used. So what happens is that like the soil water potential, leaf water potential also gives us the indication that whether sufficient amount of water is present in the plant or not. So this is basically a method of destructive sampling where the leaf is taken and placed in the pressure chamber which is closed, and from the cylinder the gas is released into this chamber, and by slowly increasing the pressure of the gas within this chamber, the point at which the leaf releases the water or there is sap exuding, we can measure it with the help of a pressure gauge. So at corresponding pressure at which the leaf tends to release the water from the or the water is released from the leaf, That corresponding measurement or the pressure measurement in terms of bar gives us the idea of the leaf water potential. Now, lower potential indicate that there is greater need for water. Although this method is not very common and it requires intensive training and time to obtain reliable results. So, this is an indirect method of shielding of irrigation, but not a very common method. Now, the critical stage approach method, which is a very common approach used by the farmers and also some researchers. Here, basically, for each crop, critical period have been standardized at which it is crucial to apply irrigation or the plant is sensitive to water stress. And if the water is not applied at these particular stages, the plants may suffer huge yield loss. Here is a list of the critical sensitive stages important for different crops. Most commonly in wheat, we all know that crown root initiation is a sensitive moisture sensitive uh, crop growth stage where if irrigation is not provided, then it can cause significant reduction in the yield of the crop. Simultaneously, there is a list for all different kinds of crops and with the different moisture sensitive stages. So at last, we can summarize that soil indicators, plant indicators as well as the climatological indicators, a combination of these are very efficient research tools for devising irrigation scheduling and also providing advisories to the farmers. Some of the simple methods like critical crop growth stage, field and appearance method, or maybe the evaporimetry method, soil cum sand mini plot technique method, or sowing high seed rate are very easy to set up in a farmer's field or set up anywhere and provide advisory, but this won't give the actual figure or give the actual water savings. So if we want to get the actual water savings, we need to do the soil water budgeting so that we can specifically determine that when there is need to irrigate and also how much irrigation we need to apply per irrigation. Now the main advantages with shielding of irrigation is that it gives us improved yield with less water and it also helps us in utilizing the rainwater efficiently. Moreover, shielding of irrigation also gives us reduced energy cost for pumping the water and also saves the labor cost. It reduces the leaching of the nutrients from the soil root zone, it improves the soil quality, etc. Here are some of the references. At last, I would like to say development that meets the need of the present without compromising the ability of the future generations to meet their own needs. So, judicious irrigation makes it possible. Thank you.